This video primarily showcases a research endeavor by Professor Zhuang Yaoming from the Machine Vision Laboratory at Northeastern University, published in TIM2023, entitled Amos-SLAM, an Anti-Dynamics Two-Stage RGB-D SLAM Approach. In recent years, the increasing demand for robots from humans has driven the development of the robotics industry, with simultaneous localization and mapping SLAM being a crucial technology to enhance robots' perception capabilities. The localization and mapping functions of SLAM, as demonstrated in the animated image, involve the robot knowing its position in the scene and creating a global map. The primary focus of this paper is to address the impact of dynamic objects in dynamic environments on the localization system. As shown in the video, the movement of dynamic targets affects the effectiveness of the system's localization. As depicted in the video, by eliminating the dynamic features of dynamic targets and relying on the features of static targets, the SLAM system significantly enhances its localization capabilities in dynamic environments. The main framework of the paper is illustrated in the figure, where the system takes adjacent frame images as input and performs instance segmentation and visual geometric segmentation simultaneously on each frame. Known dynamic targets are handled through instance segmentation, while unknown dynamic targets are processed through visual geometric segmentation. The potential motion regions obtained from segmentation are subjected to motion discrimination. For actual motion regions that are not detected through motion discrimination, feature points within the regions are extracted to mitigate their impact on the system's localization. Ultimately, the influence of both known and unknown dynamic targets on the SLAM system is eliminated. The primary method employed in the paper involves a key innovation of handling dynamic objects after classification. Initially, dynamic objects are classified with common dynamic objects in the scene categorized as known dynamic objects, and instance segmentation used to separate these objects from the surroundings. For unknown dynamic objects, potential motion regions in the scene are segmented through superpixel and clustering. This method effectively identifies all potential moving targets in the scene. The potential motion regions are further examined for their motion status using epipolar constraints and reprojection error. The principle of motion verification is illustrated in the figure, where the reprojection error for the static point P and the dynamic point P are denoted as D and D respectively. It is observed that the reprojection error for dynamic points is greater than that of static points. In the TIM dataset, dynamic targets identified through dynamic inspection are depicted in the figure. The first row showcases the static features retained after the removal of dynamic characteristics. The second row represents the identified known dynamic targets, and the third row illustrates the identified unknown dynamic targets. It is evident that even the chairs being moved by individuals in the scene can be detected. Experimental results in real-world scenarios involve testing the segmentation performance under varying speeds. It can be observed that instance segmentation and other deep learning methods may fail when the motion target moves too quickly or too slowly. The image on the left compares our method with orb's trajectory on the TIM dataset, showcasing a significant improvement in localization performance after removing dynamic targets. On the right, the image compares our method with ground truth, demonstrating a close resemblance between our method and the ground truth. By comparing the root mean square error RMC of various evaluation metrics such as 8RP, our method achieves the best performance on the TIM dataset. In summary, our main contributions include the proposal of a real-time semantic RGB-D SLAM system tailored for dynamic environments based on RG-SLAM. Additionally, we introduce a two-stage dynamic detection method that integrates instance segmentation and visual geometry segmentation to achieve better segmentation of dynamic objects. Lastly, experiments on the TIM dataset demonstrate that our method achieves state-of-the-art performance.